Hi, Luis. Welcome to the podcast Everyday Metallurgy.
Thank you for the invitation, Peter. How's it going?
Very well. You are my first guest from Mexico,
Is that so?
and I'm very curious to first learn more about you, but then to talk about sheet metal and forming processes of that, focusing on stamping processes. But first, would you like to introduce yourself, your name, your background, and what you
Sure,
do in your daily business?
sure. As you have already introduced me, my name is Luis Palomera. I am mostly have been developing myself in the auto industry for the last, it's already 22 years. Yeah, only a bit. I have a bachelor's degree in metallurgy from it's called UNAM. That's my alma mater. I studied back in 2001, so it's a bit already some time.
Yeah.
I've been mostly, as I mentioned, in auto industry. Currently, I'm working in Tata Steel, which is the 13th biggest steel maker in the world. Previous to that, I was a materials engineer at Nissan. I was there for almost 6 years, and before that, just a couple more small suppliers for springs and that kind of stuff. But I've been around the block for a bit already.
Yeah, and your daily task is you're not producing the steel, but you are advising and helping customers understanding the properties of it and how to improve the quality and how to improve the quality of the products. And we talked about this when you have to make a door for a car, you have to stamp some holes, you have to make some sheet forming, and
Yes.
And sometimes it can be difficult to understand what is the stamping. Why is that an issue? Can you bring some light on what is the stamping about?
For sure. I think if I may allow me to show a small short video, so we can understand what, as you say, what's stamping.
Yeah.
So let us begin. I'm going to show you a short stamping process.
We go.
Okay. So this is a very general stamping process, what we call a tandem press line. There are 3 different types of stamping. This is the one that's used for very big parts. You just mentioned a door. So this would be the process normally used for producing doors. As you can see, it's several different stations. Robot arm loads what we call a blank, like a piece of steel with a specific, silhouette. And it gets transformed into a specific shape in several different steps. Normally, we think 5 or 6 steps. As you can see, the speed is comparatively low.
Yeah.
You get some stuff gets cut out.
Yeah.
And then an arms. This one, for example, I guess it's pneumatic, so it sucks the part. So it adheres and then it moves back.
Yeah. And I could see there were 2 sheets in the same press. Is it to save time to make things
well, let's say let's think about I don't know, the fender in your car. Your car has 2 fenders, right? Left side and right side. Why not make it both at the same time?
Okay. Yeah.
It makes it cheaper, right?
Yeah. And then this looked like sheet thickness. What is that? 0.3, 0.5
0.7 usually.
Okay, that's the thickness of a car sheet.
If we're talking those, yes, 0.7 millimeters, It's very common for what we call exposed parts. Exposed parts is something that you can see: the bonnet, the body side outer, the roof, the doors, the trunk, that kind of stuff. Usually is that thickness.
Yeah. I remember some years ago we had a product around the size in stainless steel, and it was stamped, but it was for a pump that was submerged in the ground. So the pressure was maybe 8-10 bars, and therefore it had to be quite thick. So I think the thickness was about 5 millimeter.
Oh wow!
And it was fine stamped.
Yeah.
But our supplier didn't want to make it because it was so difficult.
Yes.
But can you imagine what makes that difficult? And can you explain why they might not be interested in doing it any longer?
Yes, and actually, I have a short clip regarding fine stamping, because when we see the video I just showed, you may have noticed that when the press comes down, there's some spoilage, if you want to call it like that, some stuff that gets cut out, some extra sections of the sheet metal. When you're talking fine stamping, it remains the same size. You don't cut anything out. You may do a hole in the middle of the strip or whatever, but the edge, the border area of the part must stay the same. So it can be fine blanking. And in fine blanking, the thinner, the easier. It's a very difficult process. But when you're talking 5 millimeters, if I were your supplier, I think I would have answered the same, to be honest.
Yeah.
Is
it because the power you put in is so large that you make deformation and therefore it changes shape?
Exactly. Let me show you a quick clip of the process. So this is a fine blanking line. I'm not sure what type of part it is, but as you can see, it's a very small component.
Yeah.
The scrap or the amount of metal that is removed is small, and the tolerances are very, very, very tight. So it's a process, as you can see, that runs way faster than the one we previously saw. Of course, the cost of the component, if you consider kilo by kilo of the component itself, it is way more expensive. So it's a challenge to make this kind of parts in a sustainable way. It's not that easy.
No. Now we have seen two different ways of doing it, and the tooling looks very different.
Yes.
The door tooling was one big chunk of a tool piece, where the other would look like a following tool with many different tool sets, making each one progress in the process. How would you describe this tooling? What is important for the toolings to work?
So you just hit the nail on the head. The main parameters of a stamping process, well, of course, there's the material, right? The thickness, the mechanical properties, the type of steel, and all that stuff. But let's talk about the machines themselves. You have the presses, as you just mentioned. They can be very big presses, and of course, the bigger, usually the tonnage that they can apply to the sheet is higher. For example, the ones that we saw at the beginning, we may be talking about, I don't know, 10,000 ton press.
Okay.
So it's a monster.
Yes.
When we go to the other one, the fine stamping one, that one may be 150, 300.
Okay. Yeah.
So it's a very small one. Another important parameter is the process speed. Normally, process speed is measured in hits per minute or strikes per minute. what we call SPM. So
Yeah.
every time the tool goes down and then up, that's a strike. So you see, pa, 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 pa. The tandem press was very slow. We may have had, I don't know, 10 strikes per minute. And in the second one, as you say, there were several, we call them stations. And each station makes something different to the strip and then converts it to a final part, right?
Yeah.
So that's just how it is. Depending on what you're looking to produce, is the kind of press you choose. Of course, you are not ideally you're not supposed to purchase a press for a single product. You're supposed to make several different ones on a same machine. But it's quite an interesting challenge to properly adjust and properly optimize this mix of materials and tooling and presses. It's not that easy.
Yeah. I maybe one more parameter in that. I remember some years ago there was a lot of debate about the lubricant
Oh, yes.
you put in because the best lubricant in the world contained some substances that were cancer could cause cancer. What is the status of that today? Is it still used, or has they found something different?
I mean, every time I hear somebody saying something about something that could cause cancer, well, don't drink the lubricant, right? As long as you don't drink it, you don't get cancer. But I know where you're coming from. It could be dangerous if you are fully exposed to it each and every day. In the past, and I have been to some stampers. Some people used to use pork lard as lubricant. It was a very smelly process, for sure, but the process was okay. But I mean, from a health and safety point of view, it's not the best option. It's the cheapest. It works
not for the pork,
okay.
at least.
Yeah. But health and safety wise, you're mixing food with an industrial environment. So strictly speaking, we shouldn't do that. Lubricants, I'm the first to declare I'm not a specialist in that. I know only the very basis of it. You can divide lubricants for automotive usage in the standard oils, either mineral or synthetic, similar to the stuff that you put in your car. And what we call the new wave of lubricants, the second generation lubricants, that are called pre-lubes. So the material comes already with like a small coating.
Okay, it's on the sheet already.
It can be, yes. It can be in liquid form, which is like the historically known version, and it can be like it looks like soap, honestly, as if you took soap and put it on the surface. And it's phosphate based, so it's not unlike a soap, and it aids in the forming of the material.
Are there also processes where you can sheet form or stamp without lubricant?
I mean, you can. I wouldn't suggest it, but when you say can I, for sure you can. Let me show you another different pressing style. As I mentioned, we saw the tandem press. What I'm going to show you is called the transfer press. And maybe you can see, can you see the video correctly?
Yeah, it runs.
Okay, so I guess you can see why it's called transfer. There's a couple of guides at the side of the tool. It picks up the part and takes it to the next station, to the next stamping step.
Yeah.
Let me play it again just for the sake of it. Yeah. So the railings have like fingers. They take the part, put it on the next step, and then go back. And that's, I mean, it's obvious now why is it called transfer.
Mm.
And as you can see, and as you very well mentioned at the very beginning, it produces mirror parts, left and right.
Mm.
That's what we call a transfer press. So you were asking about the complexity of the tooling. I guess we can now very easily see that the tooling of a transfer press is somewhat simpler than a transfer
Mm-hmm.
because it has
Yeah.
less moving parts.
Mm.
And the progressive die, it could or could not be more complex based on the shape we are trying to form.
Mm. Yeah, but the reason why I asked this about the lubricant or without lubricant was that in my former life, I was developing tool steels.
Oh,
And we were trying to develop tool steels for stamping or sheet forming that contained nitrogen, because
ah,
nitrogen is known as an anti-adhesive.
yes.
So if we could add the nitrogen in the steel, then even when you have wear, you
Mhm.
still have the nitrogen there, and it just continues coming out. So you can reshape your tool
Yeah.
and run again. Uh, have you any experience with different kind of tool steels? Is it a standard cold form tool steel like the D2 material you use, or is it special
Mm,
for these applications?
no, I mean, tool steels, you know these way better than I do.
Mm,
For example, the D grades, I think, goes from D1 to D4 tops. What makes the difference, in my experience, is the surface treatment. You can have just as produced tool, just the D1 surface.
yeah.
Maybe
Yes.
you want it to last longer,
Mm,
but then you can chromate the part, and it puts a hard chrome coating
hmm.
that resists wear better than the steel itself.
Yeah.
The technology you just mentioned, I may be wrong, but correct me if that's the case. But we call it nitriding. You
Hmm.
generate a small nitrate iron nitrate coating that
Yeah.
is very hard, and
Hmm.
again, this makes the tool with a higher wear resistance. So honestly speaking, is more a question of budget. You have money
Mm,
to properly coat your tools. How many strikes do you want them to last? You
mm.
know this again better than I do. Uh, Tools are measured in million strikes.
Yeah.
That's their lifetime. So
Mm,
I want a tool that lasts 1 million strikes.
yeah.
Okay, if you want that, then you should put some chrome on it. If
Mm,
it's only a tool that is going to produce, I don't know, 10,000 strikes, you can leave it as is.
mm,
So, it depends what you want.
yeah. Uh, then if we look at the sheet itself, uh, typically when you roll a sheet, you have anisotropy. So you have the
Yes,
rolling direction and you have the transverse direction. And that
yes,
means when you form it, it doesn't change the shape. You cannot sheet form it uniformly. So there will
no,
be a different, what is that called,
performance.
deformation
Uh-huh.
in the X and the Y direction.
Yes.
Uh, what can you do about that? How can you control the microstructure in the sheet itself? Uh, and you code it sometimes. Do you also heat treat it sometimes to make the microstructure even easier to shape?
So what you are touching now is what we call the parts design. So the auto engineer that wants
Mm,
to make a door
yeah.
says, I'm going to make a door that has this very beautiful shape.
Mm,
So I require steel that is able to be deformed without breaking, of course. so that my very beautiful door can be produced 10,000 parts at a time,
Mm.
and then comes back with this wish list, if you want to call it like that, and
Yeah.
asks the steel producer, please make something that works for this.
Mm.
We may or may not have something for that, but without going into the magic of steelmaking, yes, of course, microstructure, I would say, is the main player of this. If you want a specific set of mechanical properties, the way it bends, the way it stretches, the
Mm.
way it resists before breaking, you need to fix the microstructure. And the way to fix a microstructure to any metal component is by doing a heat treatment.
Mm.
So answering this question you made, every steel material, every flat sheet is heat treated during its production. Of course, different grades have different heat treats. I mean, that's obvious.
Yeah.
But
Yes.
everyone, in the end, a heat treat is you heat something and then you cool it, right?
Mm.
I mean, at the bare bones description, that's where you,
Yeah.
you you heat it and then you cool it. So
Mm.
that may happen maybe twice during its production run.
Mhm. Yeah.
If you want to
And
select, oh, come on, yes.
yeah, and the main reason for heat treatment is to make recrystallization, I guess.
That's one,
Um,
yes.
and I remember I have seen a sheet where my guess is that something went wrong and they heat treated it once again.
Oh, yeah. I
So
mean,
there were grain growth.
yeah.
Is that something that happens, or is it a oops?
It is an oops because the cost of that specific coil would go up, right?
Mm.
Uh, and I wouldn't feel comfortable guaranteeing its properties again.
Mm.
So when that happens, we call that recirculation.
Mm.
You may downgrade the steel. If it was
Okay.
a premium steel for cars,
Mm.
then this recirculated steel may go down, and now
Mm.
it's steel for construction, say.
Okay. So for a refrigerator.
Let's say that, yes.
Yeah. Yeah. Mm. Um, and if we look into the
Mhm.
microstructure, how much do you adjust it in the process, and how important is it towards the stamping process? So
Okay.
do we have a window this size, or is the window that big? I
Uh,
need to understand a bit about that.
I'm going to ask you something that may come out of left field, but
Yeah,
please bear with me. What's your favorite fruit?
an orange.
An orange. Ah, I was hoping you would say bananas.
Yeah.
And let me show you. Can you see my
uh,
screen?
yes, the
Okay.
material banana.
Ah, and that's what it's called, a banana chart.
Yeah,
So,
I made an episode about TWIP steel.
there you go.
So I have used it myself.
There you go. So, the microstructure defines the mechanical properties or the performance in the press of the
Mm.
material. The banana chart shows different families of materials. So,
Mm.
for example, you were saying microstructure. When we're talking about steel, you have your ferrite, you have your perlite, you have your bainite, you have your martensite, and
Mm.
these families, that's what they're saying. For example, this one, the one that says ZP, this is a double phase material. Double phase, but it means that it has two phases.
Mm.
One is ferrite, which we know is a soft component of steel, and you have the very hard one, a martensite. So when you
Mm.
mix a microstructure that has ferrite and martensite, you get the best of both worlds. And
Mm.
that's why by tweaking the chemistry, you can have double phase grades that can go from an elongation of 30% or strain. I don't know. I don't know
Yeah,
which
yeah,
which word is best suited for you.
yeah.
With a strength of 500 megapascal,
Mm.
uh, or in the other edge, 10% elongation, and almost 1.5 gigapascal. So
Yeah, that's a lot.
that's a lot, and that
Yeah.
I wouldn't want to try and make parts out of that kind of material. It's a mess. But
Yeah.
I hope this answers the microstructure. When we are taught metallurgy, you are taught a very simple concept, what we call the metallurgy tetrahedron. Uh, in each side, it's there's a property. So you talk about the chemistry of the material, the chemical composition. You talk about the way you make it. You talk about the mechanical properties you want it to have, and you talk about its microstructure, because all those 4 points are connected. If you want to move one of those, you modify the others.
Yeah. Mm.
Yes.
Yeah. I became curious now. You had the TWIP up there. Is TWIP in use in sheet forming in cars today?
I know a few automakers that are using it. It is not a very noble material. It's very difficult to use.
Yeah.
It has a lot of carbon. It has a lot of manganese. So
Mm.
with the carbon, it's difficult to weld.
Yeah.
With the manganese, it's difficult to paint.
Uh-huh.
So
Yeah.
is it used? Yes, of course. It is very expensive.
Mm.
Not a lot steel mills are able to make it. Some we are, for example, we are able to make it, but it's so difficult that we have not optimized, so it's very expensive for us. So
Yeah.
from a commercial sense, it doesn't make a lot, a lot of
Yeah.
point to go pedal it.
No, I heard that maybe it was the first generation TWIP, but it had the disadvantage that when you shaped it, you could shape it because it has very long elongation. But after shaping it, it was aging. So after a year or two, it started to get brittle
Yes,
because you could only deform it once.
yes,
So therefore, you have to sheet form it in hot condition, in
yes,
red condition.
yes,
Is that still so?
yes.
Okay.
Unfortunately, it is. It's as I mentioned, it's not a noble material. It
Mm,
requires specialized equipment. It requires specialized suppliers. Not a lot of steel mills can make that kind of material.
mm,
Let me, for the people listening to us, let me show you what are you referring to hot deformation.
mm.
It's what we call hot stamping.
Yeah.
So this is the material in sheet form.
Mm-hmm.
It gets, cut into a simple shape.
Yeah.
It gets sucked by a robot, and it goes into a furnace. The
Mm-hmm.
furnace heats it up to, I think, 950 degrees
Wow.
Celsius. Yeah,
Mm-hmm.
it comes very hot.
Yeah.
It gets taken out,
Mm.
and it goes into a press. And in the press itself, you deform it and you quench it. It's already
Ah,
been cooled with water.
yes.
And well, there's this guy checking if all the parts are okay.
Mm.
So as you can see, compared to the processes we just saw, this requires a lot more investment, because you need a furnace, you need
Yeah.
robots that can withstand almost 1,000 degrees. So
Yeah.
can it be done? For sure, it is being done right now. But
Yeah.
is it simpler? No, and it's way more expensive.
Yeah. And I could imagine the tooling are also at another cost and another materials than you do with the cold forming.
Yeah,
Uh,
yeah. The
are they integrated with cooling channels?
yes, they have. How would you, it's like copper cooling channels. So you
Mm-hmm.
run cool water through it.
Yeah.
And of course, we know that copper is a very good heat conductor.
Mm.
So it extracts all that heat, removes it, and the water itself goes into a heat exchanger to cool it again, and pop goes the whistle, you know.
And recycle, yeah.
Yeah.
Yeah, fantastic. Now we have seen many parts for cars, but to give some insight in how would the world look if we did not have stamping and sheet forming?
Oh, wow.
How important is it for the world to run?
Oh, I mean, does your chair, the one you are currently sitting in, has any tubes, like for legs?
Yep.
I don't mind those. So that's a stamping for you. Some sort of stamping. I guess we both have a fridge at home.
Yeah.
You have a washing machine. That's made of stamped sheets. We do have maybe air conditioning. We have, I don't know if we're working. No, we have, if you can look at my windows, all those aluminum profiles are bent, are stamped. So everywhere you look, you can see stamping. All the railings, for example, on the edge of a building, that kind of stuff, those are stamped. So it's ubiquitous, I guess you can say.
Yeah. So do you have some idea on how they produce almost is it 2,000 million tons of steel per year in the world?
Oh, wow.
How big a percentage goes to stamping processes? Is it half?
No, I would say half goes to construction of one way or other, like construction wire and plate, that kind of stuff.
Yeah.
It's just I'm talking just as an educated guess. I would say maybe 30%, 25% of the whole production goes into stamping of some form or other.
Yeah, it's still a lot if it's 500
Oh,
million.
it's a monster amount. So, yes.
Yeah, yeah. It's difficult to understand those numbers. It's
I cannot imagine
really,
them.
really big. Yeah. So my final question, Luis, is
Yeah, sure.
where do you think stamping processes will be in 10 years from now? Will it be the same? Are we on the top of the S-curve and we do not see any innovations, or are there still jobs for people like us to do?
I really hope there's still jobs, But, I mean, process-wise, there's always innovation. Hot stamping was impossible to imagine 20 years ago. So, I mean, some visionaries ask the same questions you are asking now. How about we heat the sheet before we deform it, and then hot stamping comes along. Some people are now developing, I have read somewhere, what they call warm stamping. So not ambient temperature, not high temperature, but something in the middle. They are using also what they call rubber stamping. Instead of using metal tooling, they use like small rubber cylinders, and they go down like there are 100 or 200 rubber cylinders, and then they go down into the sheet and shape it. So there's a lot of.
Yeah. Is it because you can change the tool by removing these rods? So you have a multi...
you can control them differently in each section.
Yeah.
I guess the maintenance or the consumables cost would go lower, because if something goes wrong, you just remove the stepper, the rubber block.
Yeah, I could imagine a tool to make a door in a car that is $100,000 or something like that, or maybe even more.
Yeah. That's not out of the park. That's a very common price. So if you can make a cost reduction of 10%, that's a lot of money.
Yeah.
That's a monster amount of money. So any innovation, even that could be considered, comparatively small to a full tool redesign, makes a big stride towards, optimizing the process.
Yeah. Um, I have one more question. Sorry.
Please go on.
Yeah. Most of these sheets, are they coated? Are they galvanized before stamping when they go into cars?
That's a question of design philosophy. For example, I'm going to speak from a Japanese point of view because that's mostly where my experience comes from.
Mm-hmm.
The Japanese divide the world in 3 regions based on the severity of the corrosion that happens while you're driving your car.
Okay.
So, for example, the corrosion performance that you need in a country in which it snows every year and you salt the roads is
Yeah.
not going to be the same as here in Mexico. I think we have had snow in Mexico maybe twice in 100 years. So
Okay.
the corrosion performance is nowhere near,
Mm-hmm. Yeah.
So for Japanese OEMs, for example, they think they consider the harshest environments in Canada and the US.
Yeah.
Afterwards comes Europe.
Mm-hmm.
So I guess you are familiar. And
Yeah.
afterwards,
Yeah.
where they
I
call,
live in the northern part of Europe where we have
there
snow
you
and
go.
a lot of salt every winter, even if it's not snowing. But here, temperature are typically at night below 0 degrees,
Hmm.
so it's freezing. And
Hmm.
then during day it comes up, then goes down again. So when it's up, water comes on the street.
Yes.
Then when it freezes, they have to salt it. So
Yeah,
very
it
often they
ices.
salt it every night.
Hmm.
Mm.
So there you go. I cannot imagine that happening in Mexico, for example. So
No.
so the corrosion requirements for the car itself are completely different.
Mm.
So a floor, the several parts that comprise a floor are galvanized for European market,
Mm.
for the North American market, Canada and the US, but
Mhm.
such requirements are actually not needed in a warmer temperature because you don't
Mm.
get that harsh environment.
Mm.
So it depends.
Uh, yeah. So then we comes to the real question. That's
Okay.
recyclability, because that is the big theme now to go electrical furnaces, but then we need to recycle more.
Hmm.
Uh, how do you see recycling of stamp products if you compare it with the uncoated and the coated version?
So this recycling is not a new thing. It has been happening for the last 20 years. On the first process we saw, the tandem process, you saw there's a lot of wastage. There's a
Yeah.
lot of sections that are removed. Those
Mm.
ones are compacted into cubes, and
Yeah.
those are sold as scrap. Of
Mm.
course, you need to, as much as possible, try to separate coated and uncoated products
Hmm.
because the cost of the scrap itself is different,
Mm.
and you cannot be mixing them because the zinc is not something that should go into the steel but on top of
Mm.
it. So
Yeah.
if you have scrap with high zinc content, maybe you need to remove the zinc first, so that's an extra
Hmm.
process.
Mm.
So it makes the value of the scrap go up, go down.
Yeah.
But there are companies that I would say no longer purchase a lot of iron ore but scrap and then fuse it and then make sheets again.
Mm.
And again,
Yeah.
it goes into the
Uh,
merry-go-round.
yeah. I have a funny story. When I was finished my studies, I was employed
Mm-hmm.
at the steelworks in Denmark,
Mm.
and we were also purchasing these blocks, compressed blocks,
Mm-hmm.
and exactly as you say, the uncoated material was more valid because it was cleaner
Yes.
iron. But they were called ladder blocks
Okay.
because the old car factory in the Soviet Union, the Lada brand. I don't know if it exists any longer, but they were the only car producer in Europe or in our area that did not galvanize. So therefore, the rumor or the joke was that the highest value of a ladder is the ladder block.
Uh, you would be surprised they are still around. And finally, they have modernized their looks because the Lada looked the same for 40 years.
Yeah.
They don't have a lot of models. It's a comparatively small OEM, but they have 2 or 3. And I think the Top Gear guys made some review of one SUV. I think
Uh-huh.
you may want to look in YouTube for it.
Yeah, I will do that. Yeah. Thank you. Luis, I really enjoyed our talk, and
Appreciate it.
I learned something new. This hot stamping, I've never seen that before. So thank you very much for sharing with us.
Anytime.
Yeah,
Glad to be here.
yeah. If people want to learn more about this, what do you recommend? Are there special papers? Are there conferences? Where should they go?
What I did back in the day was to join associations.
Mm,
I'm not familiar with the ones in Europe,
mm,
but the ones here in the Americas, it's the American Society for Metals, the ASM,
mhm. Yeah.
the AIST, ASTM has also some stuff related to this,
Mm,
and most of them have public websites. You don't have to be a member to
mm,
to get to know some of the general stuff. And
mm.
even if you want to invest a bit, if you're a student, I guess the fee is like $30. So it's not that much money for a lot of knowledge.
Yeah, that's a good idea. And of course, the highest platform to learn from is the podcast episode we just made.
But well, yes, of course.
Yeah, yeah. Luis, thank you very much. I really enjoyed it.
Thanks for the invitation, Peter, and let's hope we can do this again. I had a lot of fun.
Thank you. Bye.
Cheers.